Hello and welcome to Recitation 6 for fluids. Today we're going to be looking at two problems. The first one is on Bernoulli's principle sort of stuff, and the second one is going to be the energy equation with Reynolds transport theorem. And so for this first one, we have a jet of water that is discharging vertically upward through this nozzle right here. So the nozzle exit diameter is 2 centimeters, and the reservoir water level is 2 meters above the nozzle exit. The jet supports a plate, which is 500 grams, half a kilogram. I know what the plate is constraining, blah, blah, blah. You may neglect viscous effects in this problem. Density of water is 1,000 kilograms per cubic meter. Okay, so since I already said this can be relying on Bernoulli's principle, we can think about it like this. Whenever you think about having to use Bernoulli's principle or anything like that, if you can look at a problem and see, okay, so this is kind of our area of interest over here. We've got the nozzle exit, and for this case, it's kind of, oh yeah, dude, I forgot this sucks. Ugh. I have to do this. So, yeah, we're gonna say that this whole thing is our exit right here. And it's my marker, dude. This whole thing is our exit right there. It's kind of drawn poorly, but whatever. So yeah, this is where the water is coming up out of. We're also just gonna say this extends all the way here, where it touches the plate is also 2 centimeters. Okay, so we can see that, and so this is our point of interest. I'll call this point 2, and this will be like point 3 over here. This is point 1, right? And you can see, if you want to draw it, if you imagine taking a snapshot of like a single water molecule as time goes on from this point, you can see it all follows just one same streamline all along here, and then goes up and hits this plate, right? If you can do that, that's kind of the main precursor to being able to use Bernoulli's equation. Strictly speaking, you also need it to be like incompressible, inviscid, and steady, which this is all of those things. We just said we can neglect viscous forces. And we're dealing with water, which is incompressible, and there's no time rate of change with anything. We're imagining this is an infinitely large reservoir, so there's no real volume change. You know, it's like draining a lake out of a 2 centimeter pipe. Sure, there is some volume change, but you don't care about it because it'll take forever to do anything. So anyway, first things first, we've got water shooting up out of here, but we don't know what the velocity is out here, okay? And so we can get velocities from Bernoulli's equation. So basic Bernoulli's equation, you know, it stems from like conservational momentum stuff. And you'll see in a couple different ways. The way I'm gonna write it here is it's called the head loss form of it. Everything's in meters. The primary unit that you spit out is meters. So it's like, you know, P1 over rho G. Actually, whatever. That's V1 squared over 2G plus Z1 equals P2 over rho G plus V2 squared over 2G plus Z2. And I'll rewrite this down here. This is just the general form of it. Kind of looks gross, but my bad. I didn't want to write it too far over. So anyway, and also we can see, okay, so at every point on here, I'll spoiler alert, every point on here is exposed to the atmosphere, okay? This is P atmosphere up here. The water is just leaving the nozzle right here, so that's atmospheric pressure. And then it's also still exposed to the atmosphere because it's just hitting a plate that's exposed to the air. So all the pressures are all the same, so we're just gonna take all gauge pressures. So we can just say P1 equals P2 equals P atmosphere, so those go away. And like I said, the velocity in this giant reservoir, it's not really, you know, there's no real change. So at this point, we can call the velocity 0. We can say it's just not moving. It's, you know, it's Lake Michigan or something, right? That goes to 0. This is our datum point right here, coming up here. See, right there. So we can say Z2 equals 0. So this equation gets really easy. So we got Z1 equals V2 squared over 2G. Solve for V2. V2 equals square root 2G Z1. And we know everything, just plug in the numbers. We end up getting V2 equals something to the tune of 6.26 meters per second. Any questions there? Pretty easy. Like I said, Bernoulli is your friend. It's nice. Okay. So now, for the second part, we need to know the actual force that's hitting this plate, because we know there's going to be some force balance here. We've got the weight of the plate acting down and the force of water hitting it, right? And so, I don't think I'm going to draw out the whole conservational momentum equation. You guys know it, you know. CS, rho v dot n, blah, 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 right? Everything's steady, all that stuff. We're just gonna approximate it. We're gonna do the rho v squared times A equals the weight of this plate, okay? So the external force that we're dealing with is the weight of the plate acting down. So I'll say W plate equals mg, right? Mass of the plate times gravity, okay? So we're gonna have W plate equals, in this y direction, so we've got the weight of the plate acting down, then the force of the water coming up, right? And force of this water, that's the, rho v squared times A. So we're gonna have equals rho, and this is, so, we've got rho, and hitting this is the velocity at 0.3, v3 squared, rho v3 squared times A. We're going to be solving for this velocity, because we know m and g of the plate. M is, 0.5, so W is like 4.905, equals 1,000 is v3 squared times this area, this is still the same 2 centimeters, so 0.02 squared over 4 times pi is the area. Okay, solve for V3. End up getting V3 equals 2.49 meters per second, which makes sense. It's higher up. Obviously, there's gravity pulling it down. So what did I say, 2.49? Yeah, 2.49. Okay. Cool. And that, I just, like I said, I didn't write off the full conservational momentum equation. You guys have seen it 100 times at this point. You already took the exam on it. You guys know what conservational momentum looks like. So there's that. All right, now we're pretty much ready to do the last step, which is just take another Bernoulli's equation. So again, we're going to take P1. Technically speaking, we could take P2. We know everything about P2 as well. But P1 is so nice because you can just cancel out so much stuff. So I'm just going to use P1 again. So from point 1 to point 3, let's do the thing again. I'll do it over here. We've got so now, like I said, the pressure is still canceled. Everything's just exposed open atmosphere. V1 is 0. Z1 is not 0. V3 is not 0. And Z3 is not 0. Z3 is actually what we're solving. Oh yeah, I forgot to say. The thing we're solving for in this problem, they don't even say it. But we're solving for this height here, how high the plate is from the water. So I'll call this H, or how high the plate is from the nozzle. That's what we're solving for. So we never wrote it in the problem statement. But I thought it's probably pretty confusing. They're just like doing a bunch of numbers for nothing. Anyway, cool. All right. So anyway, we end up getting Z1 equals V3 squared over 2G plus Z3. Okay. And this Z3 is this H that we're solving for. So I'll move it over. Z3 equals, let's see, Z1 is 2 minus 2.49 squared over 2 times 9.81. Okay, solve that. Z3 ends up being 1.6, 1.68. And so that equals H. So H is what we were solving for, 1.68 meters. Cool. So this plate is being held up 1.68 meters above this nozzle just by the force of the water pushing on it. We found that out using two Bernoulli's principle and a concentration of momentum with many, many assumptions in there. But that's how you do that. Not too bad. Any questions there? Yeah.
So when do we need to find V2 for?
What did you need to find V2 for?
Yeah.
Actually, that's a really good question. What did we need to find V2 for? I don't think so. Oh, okay. Well, this was probably another thing that they just didn't tell you. It was probably like a part A, part B, part C type question. They just didn't write it.
Right.
So I just found the stuff that they found in the key and did it my own way. So I guess, yeah, instead of this, yeah, you don't need V2 for anything in this
So
case.
I can see if we have find the velocity at the.
Yeah, yeah, probably. It was probably something like that. Yeah, they just didn't write the full problem statement. Yeah, there's probably like part A, part B, part C down here that just got cropped out. But anyway, yeah.
Also, is it like normal to put the datum like at the release? Like you like specifically chose the datum to be like at that point so you could cancel out the Z?
It doesn't really matter. If you, I mean, technically you could pick your datum and be down here and call this whole thing 5 meters. And you just take that as your point of reference. You just, yeah, like, it would just be a little more cumbersome because you wouldn't be able to call that some 2, 0. You'd call that like 3, and then this one 5. It's like, you get the same number, but it's just annoying to have to deal with. Yeah, like, that's another thing. In a lot of these problems, you have free reign to put whatever the hell you want. You know, same thing with like control volume analysis. You can pick your control volume. How you do that, if it makes your life really hard, then you kind of suck at it, but you can pick whatever you want. So you could pick your datum to be right in the middle, and you'd have -1 and +1. But if you want to carry -1 around, your whole problem, be my guest. But I don't want to do that. But yeah, and it doesn't matter. You can put whatever you want. Okay. Any more questions? Anything else?
How do you replace the mass times gravity by rho times velocity squared?
What?
How do you replace the mg by the velocity?
Oh, this? Oh no, this is just from the conservational momentum equation.
Oh, okay.
So this is the external force. You know, the sum of F external equals, you know, d by dt, you know, integral of the control volume, blah, blah, blah. I just didn't feel like writing that entire thing. You guys have seen that a billion times. So I just said sum of external forces, the only external force is the weight of the plate, equals the conservational momentum equation, and I just simplified it all out. But this is what the weight of the plate actually equals, it's mg, so. Anyway, yeah, I didn't do any like manipulation to magically grab that from thin air. I just didn't write the whole thing out.
Good, thanks.
Anything else? Anyone want to take a picture of this? Very cool. Cool. Okay. Now, like I said, problem 2 is like almost exactly like your homework. So, yeah, should be pretty good. Is anybody gonna go try out to be ASU's new kicker? Anybody here really good at kicking footballs? Go email Coach Kenny. He'll get you a spot. All right, yeah, here's the, yeah, so I guess, yeah, okay, yeah. So here, I actually didn't live this whole thing, yeah. So part A, that's where you'd find like velocity, yeah, whatever. Anyway, whatever. Okay. So now, problem 2. Let's see, let's do a way to do it. Yeah, it's very wordy, and they didn't really draw the, they didn't draw like the diagram. So I'll go over here in this corner over here and draw a diagram. So we got a power plant that's located next to a river, and the plant steadily pumps some of the river water into its cooling system and then dumps the heated water back into the river. When running at full capacity, it rejects 50 megawatts of waste heat to the river. Use okay, so a watt is also just a joule per second, okay? It's a rate of change of energy. And so I'm gonna write everything in terms of joules per second instead of watts, because that's what our other dimensions are. Like we've got joules per kilogram, Kelvin, whatever. But all right, so what's going on in this problem? Let's say we've got this big river over here, right? A big river. And we'll say this is our control volume right here. got some river water coming in like that, and then leaving like that. And then right here in the middle, we've got coming out of a big pipe. We've got a big power plant here. And it's sucking in water, heating it up, and then throwing it back out. Okay? And then for part A, we're gonna have some sort of delta Z in here, change in height of the river, as we're slowing downhill. So that's what's going on. So yeah, our control volume is just inlet and outlet stuff right there, and then stuff in the middle, whatever. Not the biggest deal in this case. All right, so upstream of the power plant, the river has a volume flow rate of 2.5 cubic meters per second and temperature 10 Celsius. So what is the river temperature far downstream of the power plant? Once the river water and the effluent from the power plant are fully mixed, the river drops a distance of 5 meters from the upstream and downstream. So that's our delta Z, it's 5 meters. All right, and then, so coming in, we have T in equals 10 Celsius, which is 283 Kelvin. Okay. 283 Kelvin. We got delta Z equals 5 meters. And we've also got CP is 4210. And then I'll say, now notation will get kind of confusing here. So Q dot is our heat, our rate of change of our heat, okay, our energy rate of change. Normal Q is going to be our volume flow rate. So big Q dot is 50 megawatts, which is 50 times 10 to the 6 joules per second. And then density is 1,000, whatever. And then our normal Q, our volume flow rate, in this case is 2.5 meters per second, cubic meters per second. Okay, so this right off the bat, you should know if you're dealing with any heat sort of stuff, it's going to be an energy problem. So our base energy equation is that Q dot minus W dot S minus W dot V equals, and I'm not writing the time derivative term of it. I don't feel like doing that. It's steady. It says it's steady from the get-go. You'll live. That's times Q over rho plus 1/2 V squared plus GZ plus U times rho ds or dA, rho V dot M dA. Yeah. We're not room. Anyway, okay, so that's that. And there's no work being done here. There's no shaft work and there's no friction viscous work. So we can call those 0. And then also another good thing to write is P over rho plus U, our internal energy, equals CPT. And that's like a thermo-y kind of thing. He probably went over that this morning, didn't he? Did he mention that? Yeah. Cool. Yeah, I don't know why we don't just give it to you like that from the get-go. I guess that's not the full Reynolds transport theorem version of it, but whatever. Okay, so let's keep plugging. We get Q dot equals, and I'm gonna write this as like the out minus in form now. So we've got P over rho, or not that anymore. Let's go CPT plus 1/2 V squared plus GZ times, and I'm just gonna call this V again, times rho V, rho VA, I guess, rho VA in, or out, minus in, out, minus the same thing in double bracket, rho VA in. Okay, so that's our whole thing. And if you notice, like in our control volume, since it's a giant river, we're going to call the velocities all the same. Okay, obviously the areas coming in and out are the same, the density is the same. So everything in here, like if you factor this whole term in, the quantities are the same in here, just gonna get canceled over there. So the velocities go away, right? At the outlet, we're going to call this Z0, and then we're just gonna call the inlet, that'll be our 5 meters, that's our delta Z. And obviously the CPs are different. But we also know that rho VA is just equal to M dot, right? Which is equal to rho times Q, right? Rho times our volumetric flow rate. That's also nice to have. So I'll come over here and the rest of this over here. Yeah, so let's go. So now we've got, coming out, we have CPT, T out, and so Q dot equals CPT out times rho Q, right, minus CPT plus GZ, CPTN plus GZ, rho Q, right? And technically speaking, we could just straight up solve this now. We know everything else that's in this problem. We know T out, or we know T in, we're solving for T out. Yeah, let's just solve it like this, who cares? You know, you could clean this up, factor out a rho Q, and do all that fun stuff, but I mean, who cares, you know? Let's go. 50 times 10 to the 6 equals 4210 times 1000 times what, 2.5 minus 4210 plus 9.81 times 5 times 1000 times 2.5. All right, now to solve for, oh, I forgot my T out term. 4210 times T out. All right, now to solve for T out. And when you solve this, it'll spit out Kelvin. Just convert back to Celsius, subtract 273. So solving that, you get T out. Oh, it's in my hand. You get T out equals 14.8 Celsius. Right, cool, and that's far downstream in the river, you know. So we got whatever temperature coming in here, we got 10 degrees coming in here, and then after all this is mixed and whatnot, spit out down here, it's 14.8 degrees Celsius. Cool. Any questions there? I was like, take a picture of this now, just like have it right out of the room, so if you need to take a picture of that.
So you multiply the 4210 by 10 degrees, right, in that CN, or in that CPT in portion?
Oh yeah, I totally forgot that, yeah, good call. Yep, oops. That's supposed to be 4210. Well, it'll be times 283, because it's in Kelvin.
Oh, yeah.
Yeah, but yeah, I mean, essentially, sure. Yeah, I forgot that. 4210 times 283 plus 9.8 times 1.5. 9.81 times 5, yeah. Yeah, good call, that's funny, I forgot both the temperature terms, yeah. Whatever. Yeah, you got the idea though. CPT, everything. And I guess another kid was saying in one of the other recitations, you could solve this using like the MC delta T equation. I guess I didn't do it like that, but I like go ahead and do that if you want to. I just know for sure this form will work for like every type of problem like this. I'm not sure the MC delta T version will work every time, but if it works, if you spits out the same number, sweet. And turn this into like a one-step problem. But okay, everybody cool with this? I'm gonna have to erase this because I kind of ran out of room. Cool. Okay, now part B is kind of the same sort of thing, but we're just working backwards. We're going to find what our volume flow rate is for some temperature, right? So you're still, so regulations don't allow a power plant to keep the water use between more than 10 Celsius, meaning when it leaves, cannot have temperature higher than 20 degrees Celsius. What's the minimum volume flow rate? So we're finding this Q now. So I'll put this as a question mark. Then our T out is 293 kelvins. Right. And okay, so now in this case, we can call delta Z equal to 0 now, because we're just worrying right when it comes out of the power plant. And so we can say, for the sake of argument, that when it's coming out, when it goes into the power plant, coming out of the power plant, there's no change in height. We're just saying, boom, it's like right there. So actually makes our life a lot easier. So I'm gonna say delta Z equals 0 here. It's cool. But now, yeah, it's pretty much the same exact thing. So let's go do it again. So we got Q dot minus W dot S minus W dot V equals CS. P over rho plus rho N dA. And so now, you know, makes sense times we call that 0, we call that 0. And now there's no GZ term at all, everything's 0. So I'm just gonna cancel that right away, that's fine. And again, our P over rho plus U still equals CPT, so that's nice. So I'll just simplify everything out right away. No, actually I'll write this over here in light. So we got Q dot equals our CPT. Oh, and yeah, and our velocities are still also gone, so that really makes our life easy. Yeah, CPT times rho VA out minus times rho VA in, right? And so yeah, this actually gets really, really easy. And so let's just simplify everything out. I'm still gonna call this our rho times Q. I'm gonna call it like Q min or Q minimum. Let's call it Q, who cares? So let's go 50 times 10 to the 6th equals 4210 times 293 times 1000 times Q minus 4210 times Tn, which is 283 times 1000 times Q again. Okay, and now, you know, you can factor out a Q, call this 4210, blah, blah, minus 4210, blah, blah. So this really is our, you know, MC delta T equation, which is pretty easy. Just solve for Q, factor out a Q, solve for Q. End up getting Q equals 1.18 cubic meter per second. Cool. And that makes sense because the temperature, the outlet temperature is higher, so it can't be like pushing out as much water. Yeah. Cool. Yeah, super. It was pretty easy one, pretty basic one. But kind of a rule of thumb with these, since there are so many terms you have to deal with throughout this whole equation, these really aren't going to get too difficult. Like you're probably never ever going to have to actually integrate over some area if you're doing an energy equation. It'll be, you know, rho VA is what you're going to be able to simplify everything down to. And CPT, do all that stuff. These, it's just a lot of terms they have to keep track of, and it's kind of annoying. But any questions with that? I'd say take a picture of this as well, if you would like. This would be very helpful on homework. Of course, you know, we post these tonight, whenever. If not, as usual, email me. I'll put them up. Okay. Any last questions? All good? Everybody cool? All right. What a great time.